Hello everyone, in this video we will cover the section 3.1. In this section we will see determinants. So for n is bigger than or equal to 2, the determinant of n by n matrix A, which is denoted in this form theoretically, if you remember, we can write a matrix theoretically in this form Aij n by n, and we can define a determinant of a matrix for square matrices, namely the number of rows must be equal to the number of columns. Okay, so the determinant of an n by n matrix A is the sum of n terms of the form plus minus A1J determinant bigger A1J with plus and minus signs alternating, where the entries written here are from the first row of the matrix A. In symbols, we can write the determinant of a matrix in this form. Okay, minus 1 to the power 1 plus j, A1J, determinant A bigger A1 J. If we rewrite the determinant of a matrix A is given by, in this form, Aij n by n. Aij is the entry in the ith row and jth column, if you remember, and it is shortly written as, if we use the sum symbol, from 1 to n, j is changing here, minus 1 to the power 1 plus j, a1 j. As you can see, I is equal to 1, which means that we use the entries in the first row of the matrix A times the determinant of bigger A1J. So here A1J, or generally bigger Aij, is obtained. It is obtained by cancelling the ith row and jth column, by cancelling the ith row and jth column. Namely, the size of this matrix is n minus 1 by n minus 1. N minus 1 by n minus 1. We have n minus 1 rows and n minus 1 columns for this matrix. We will compute the determinant of this one, and then we multiply this result by the entry, related entry, and also we have minus 1 to the power 1 plus j. This is the general formula for finding the determinant of matrix A. For example, we have a matrix A which is 3 by 3. We have 3 rows and 3 columns. 3, 0, 2, 0, minus 1, 2, 1, 5, minus 4, for example. And the determinant of the matrix A is given by, according to the formula, J is starting at 1 to 3, from 1 to 3, A1J, first we should write minus 1 to the power minus 1 to the power 1 plus j, a1j, determinant a1j. So explicitly, clearly, it is written as when we write first one for j, we have 1 plus 1 in the power of minus 1. Therefore, we have 2, which is even number. Therefore, we obtain plus 1. So we write a1 1 determinant a1 1 minus plus, sorry, now we write 2 for j, we have 3 here. Therefore, minus 1 to the power 3 becomes minus 1. Therefore, we obtain minus here, minus a1 2 determinant a1 2. And when we write 3 for j, we obtain 4, which is an even number. Therefore, we have plus 1 for the first term. So we have plus a1 3 determinant a1 3, a1 3. And from here, what is a1 1? This is the first entry in the first row, which is 3, a1 1. Therefore, we write 3 and determinant a1 1. Determinant a1 1. First, we should obtain a1 1. What means a1 1? So a1 1 is 2 by 2 matrix. We cancel the first row and the first column, since we have 1 for I and j, if you remember the formula. So we cancel the first row and first column. The remaining numbers will form a 2 by 2 matrix. So we write minus 1 5 2 minus 4. Okay, 2 minus 4. And we know how we can find the determinant of 2 by 2 matrices. So the determinant of a1 1, a1 1, or let's write directly the result. Determinant a1 1 is equal to, if you remember, AD minus BC. Therefore, we obtain 4 minus 10 becomes minus 6. Minus 6. Minus a1 2, which is 0, times the determinant of a1 2. Namely, we cancel the first row and second column, first row and second column. So we have 0 5 2 minus 4, 0 5 2 minus 4, determinant a1 2, plus a1 3, which is 1, determinant a1 3, namely we cancel the first row and third column. So the remaining numbers are 0 minus 1 2 2, 0 minus 1 2 2. And from here it is equal to minus 18. The second one is 0, and the third one 0 minus minus 2 becomes plus 2. We obtain 20. This is the determinant of the matrix A, 20. Okay. And there is another example here. We find the determinant of this matrix according to the first row. And as you can see, we write A11 determinant a bigger A11 minus A12 because we have minus 1 to the power 1 plus 2 becomes minus 1 since we have an odd number for the power, plus A13 determinant bigger A13. So the first entry is 1 A11 determinant by cancelling the first column and first row. Since we have bigger A11, it is obtained by cancelling the 1th row and 1th column, and the remaining number will form this matrix 4 minus 1 minus 2 0. And similarly for the second term we have 5, which is the second entry in the first row determinant by cancelling again the first row and the second column. First row, second column, we have 2 minus 1 0 0, 2 minus 1 0 0, plus third entry A13, so it is 0 determinant by cancelling the first row and third column, since we have 3 here, it is corresponding to the number of column for the matrix. The remaining numbers are 2, 4, 0, minus 2, as you can see. For the first one we have 1, 0, minus 2, minus 5, 0, 0, 0 times this one, so we have minus 2 for the result. This is the determinant of the given matrix in this example. And another common notation for the determinant of a matrix uses a pair of vertical lines in place of brackets. Thus, the calculation in example can be written in this form. Instead of writing this symbol directly, we use vertical lines, a pair of vertical lines. We don't write determinant like this one, just we sketch vertical lines for the entries. So this symbol means we have a determinant of 2 by 2 matrix, as you can see. Okay. And to state the next theorem, we have a theorem here. It is convenient to write the definition of determinant of a matrix in a slightly different form. Given a matrix Aij, n by n, we have square matrices. Determinants are defined for square matrices. So Ij cofactor of the matrix A is the number bigger Cij, given by Cij is minus 1 to the power of I plus j determinant Aij. Okay, namely, if you remember the formula for the determinant of a matrix given here, the determinant A is equal to the symbol, some symbol from J is equal to 1 to n minus 1 to the power 1 plus j A1j determinant A1j. So we gather the terms, which is the first one and the last one, this one and this one, and we say this multiplication as the Ij cofactor of the matrix A, and it is denoted by Cij, bigger Cij. Therefore the formula becomes, if we write Cij for them, bigger Cij, so the formula becomes the sum symbol from 1 to n A1j C1j, okay, 1j. This is another form of the definition of determinant of a matrix A, which is n by using the cofactor, ij cofactor. As you can see, the explicit form can be written as A11C11 plus A12C12 blah blah A1n bigger C1 and by using the cofactor. As you can see, this formula is called a cofactor expansion across the first row of the matrix A. We use the entries of the first row, A11, A12, A1n. Okay, this should be C bigger C1n. So after knowing the cofactor expansion for the determinant according to the first row, in this theorem we see that the determinant of n by n matrix A can be computed by a cofactor across any row or down any column. The expansion across the ith row using the cofactors in 4 written here can be written in this form. Namely, we can use any row for finding the determinant according to the formula. Just we use the entries in the first row, but we can use the entries of the second row or third row or any row, okay, according to this theorem. So the formula for the determinant generally can be written as in sum symbol from J1 to n A I J times bigger C I J, or explicitly, clearly, it is written as AI1 CI1 plus AI2 bigger CI2 and so on. AIN bigger CIN. Okay, we use any row. I can be any number less than the number of rows. This is the formula according to ith row. If you write 1, so we have this formula, namely we find the determinant of the matrix across the first row. Or we can find the determinant of a matrix according to any column, across any column. Namely, now we will change the values of the second index in this formula. I is constant here. So this is the formula for the row. So for the column, the determinant, let's write here, of the matrix A will be where A is given generally, if you know, A, I, J, n by n. So it becomes in sum symbol from 1, and the variable of the sum will be I now, not J, to n Aij bigger Cij. Explicitly it is written as A1J C1J plus A2J C2J and so on. A and J bigger C and J. Okay, this is the expansion of the determinant, the cofactor expansion for the determinant of the given matrix according to the jth column. jth column. For example, use a factor expansion across the third row to compute the determinant of the matrix A, where A is given in this form. According to the third row, across the third row, we use the entries in the third row, these ones. So the determinant will be, let's write here, -1. So according to the first entry, namely it is in the third row, namely we write 3, plus it is in the first column, therefore we write 1, times 0 times the determinant of A31, as you can see, A31. Namely, we cancel the third row and first column. So the remaining numbers are 5, 0, 4, -1. Plus, according to the second entry, -1 to the power 3 plus 2. It is in the third row and in the second column, -2 times, cancelling the second column and the third row, the remaining numbers are 1, 0, 2, -1, plus, for the last one we have -1 to the power 3 plus 3, since it is in the third row and in the third column, times the entry times the determinant of the matrix A33, namely we cancel the third row and the third column, so the remaining numbers are 1, 5, 4, 2, 4, and from here it is equal to, the first one is 0, since we have 0 in the multiplication, -1 times -2 becomes +2, times this determinant, which is -1, and the third one is 0 already, since we have 0 here, so we have -2. Okay, according to the third row we can find the determinant of this matrix. Or if we look at our example here, let's use now a column to find the determinant. A is given by, from here, 3, 0, 2, 0, -1, 2, 1, 5, -4. So we have, let's use for example the second column for finding the determinant. So it is equal to 0, -1 to the power, the first entry of the second column is 0. Actually we obtain 0 for the first term, but to know very well the formula, let's write everything. -1 to the power, it is in the first row and in the second column, 0 the entry, times the matrix by cancelling the second column and the first row, so we have 0, 5, 2, -4, 2, -4, plus -1 to the power for -1, in which is the second entry in the second column. It is in the second row and in the second column, therefore we write 2 plus 2 for the power, and by cancelling the second column and second row, the remaining numbers are 3, 1, 2, -4. Second column and second row, yes, it is true. plus minus 1 to the power, it is in the third row, plus 2, and in the second column times 2, and the remaining numbers by cancelling the second column and third row, 3 1 0 5 0 5, and from here we have 0 for the first term, plus minus 12 minus 2 minus 14, plus minus 2 minus 2, 15, minus 2 15, okay, from here we should obtain the same formula, but there is a mistake here, I guess. 0, here we should write minus 1, we should write minus 1 here, the entry. We should not forget to write the entry. Therefore we have plus 14 minus 1 minus 12 minus 2 becomes minus 14 for the determinant. Minus 14 times minus 1 becomes plus 14, and this one is minus 2 times 15, so we should obtain minus 16. Let's look at here. Yes, this should be minus 16, minus 16, minus 16. Okay, we have the same results. Namely, you can use any row and any column to find the determinant of a matrix, and you should not do any mistake to get the true result. The multiplications are done very carefully, should be done very carefully. Okay, and lastly we explain the theorem 2. If A is a triangular matrix, then determinant A is the product of the entries on the main diagonal of the given matrix. If we have a triangular matrix, for example, if we have a lower triangular matrix, let's write 3 by 3 lower triangular matrix, 2 0 0, 3 minus 1 0, 7 6 9. This is a lower triangular matrix because all entries above the main diagonal are 0, as you can see. This is a lower triangular matrix. Triangular matrix, which is 3 by 3, which is a square matrix. And we want to find the determinant of this matrix. According to the theorem, it is enough to multiply the entries on the main diagonal, namely 2 times minus 1 times 9. 2 minus 1 and 9 are the entries on the main diagonal. So we have minus 18. We have minus 18. But let's check by using the general formula, determinant of the matrix A. Let's use the first row because we have more zeros in the first row than the other ones. It will make easier the calculation of the determinant when we have a lot of zeros. Just we are interested in the first entry because the others are equal to 0, which means we obtain 0 for these terms. So directly just I will write the term for the first entry, 2 minus 1 to the power 1 plus 1 times, we cancel the first row and the first column, the remaining numbers minus 1 0 6 9. So we have 2 times minus 1 times 9 minus 0 becomes minus 9. Therefore we have minus 80. Okay. Therefore, when we have a triangular matrix, can be lower triangular or upper triangular, it is enough to multiply the entries on the main diagonal of the given matrix to find its determinant. Okay. Thank you very much for your listening.